Hi, I'm Josh Cast. I'm Joseph Diener.
I'm Robert Jones.
I'm Easton Bornemeyer. And I'm Ollie Zergany.
And we are Team Polarization Bears in the Colorado School of Mines. And this is our video submission for the 2018 IEEE APS Student Design Challenge. Here to present to you our wideband switched array channel sounder capable of determining the channel impulse response, the power delay profile, polarimetric information, and angle of arrival in an affordable and portable package. And this can determine most of all the useful information about a channel. So this is the overview of our system. We have 8 antennas that we can switch between with these 2 8-throw switches. As talked about earlier, these have 2 polarization states, and there are 2 feeds for each antenna, which are fed into these ports, and we switch between these 2 with a 2-throw switch. All the switching is powered and controlled by the Arduino. For here, it also provides power to the amplifier, which increases our signal by 14 dB, and we run it through a filter, a bandpass, and then into the HackRF, which is our SDR, which does all of our processing, finds the IQ data, and then creates our PDPs. So these 2 all the switches and the amplifier are all wideband and can operate from 1 to 6 gigahertz effectively. The antennas and the filter are specifically selected for the ISM band, but can be replaced for whatever band you want to operate in the future. And then the SDR is connected to the laptop. The laptop provides power to the system, as well as controls the Arduino, which controls the switching, and then it uses MATLAB to do all the data processing. So here we're going to demonstrate our system's ability to determine angle of arrival and polarimetric information. So we have, again, our 8 antenna element switchable network, and each of those have 2 different polarization states. We can control this with this MATLAB on-screen graphical user interface. So here's the 8 antennas and the 2 polarization states for each antenna. So we can switch to any of these antennas that we want to, and then each of these have our polarization state. Currently, our antenna is right in front of, or the rubber ducking antenna is connected to a VNA, which is transmitting a power level or a signal from 5.8 to 5.82 gigahertz at about 100 hertz bandwidth. From here, if we look around, we can determine that the greatest response is at antenna 1. So this determines that the signal is right in front of antenna 1. So if we went to the complete back end, which is 7, it's not that great of a response as if we went to this. And then we can, since it's at horizontal, so right now we're on vertical, if we go to horizontal, drastic increase. That means that the signal incoming onto antenna 1 is horizontally polarized.
So we can see here it sets the GNU radio. It's going to acquire some IQ data, and we can see a PDP has been generated. What you can see is that while the autocorrelation is more or less trying to do the right thing, we can see the overall amplitudes that are obtained are incorrect. But we can see the basic foundational framework has been laid.
So for future improvements to our systems, our antennas and our filter were built on dielectric that we got from the student special, and which was deviated slightly from the dielectric constant that we predicted. So therefore, the matching to these wasn't the best and can be improved in future iterations with a better approximation of the dielectric constant we actually received.
Similarly, the post-processing, although it's currently an okay start, can be improved in order to ensure that there's stronger autocorrelations from transmitted PN codes, since the observed maximum PN autocorrelation is less than what we'd expect for an ideally demodulated signal. And improving this will help to improve the quality of the channel sounder dramatically.
Thanks for watching. We're
Team Polarization Bears.